Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in any college mathematics course, please consider subscribing because you are in the right spot. Let's go ahead and get into the current video. All right, drop my pen here. Take a look at solving homogeneous equations with constant coefficients, and I'm going to look at the specific case of distinct real roots. In subsequent videos, we'll look at repeated real roots and then complex roots. I'm going to go ahead and assume that you watched the first video in this series where I talk about the characteristic equation. I'll briefly remind you what the characteristic equation is, but of course that video, elaborates on that a little bit. Okay, so homogeneous equations, constant coefficients for, of course, differential equations, and this is distinct real roots. So let me first of all say, for a differential equation, a(n) y to the n plus a1y prime plus a0 y equals 0. So this is my differential equation with constant coefficients. If y equals e to the rx is a solution, then r is a root of the following polynomial equation: a(n) r to the n plus a1r plus a0 is equal to 0. And again, this is an if and only if statement. If e to the rx is a solution, then r is a root. Conversely, if r is a root, then e to the rx is a solution. That means to solve the differential equation, we have to solve a polynomial equation. So let's go ahead and take a look at some examples. First example. Let's say I want to look at y double prime minus 4y is equal to 0. So I want to solve this differential equation, and here's the solution. We go from the differential equation to the characteristic equation. So the characteristic equation of this differential equation would be r squared minus 4 is equal to 0. So notice that to go from this differential equation to the characteristic equation, I keep the same coefficients. So I would keep 1 and negative 4. The nth derivative of the unknown function gives me r to the n. And of course, a0 y, which is the constant term, gives me just a0 in the characteristic equation. So therefore, the negative 4y, which would be this term here, you can see my fingers there, would just give me just the constant term on the end. Okay, so I've got r squared minus 4 equal to 0. And of course, we can solve this polynomial equation, add 4, take the square root. That would give me r is plus or minus 2. And therefore, we know that y1 is equal to e to the negative 2x, and y2 equals e to the 2x are both solutions to the original differential equation. And since this is a linear homogeneous equation, every linear combination of those is also a solution. Therefore, the general solution to this differential equation would be y is equal to c1 e to the negative 2x plus c2 e to the 2x. So this would be the general solution for that differential equation. Now, if I was to give you an initial value problem, we could say solve for the unknown values of c1 and c2, but for now, c1 and c2 are just going to be, arbitrary constants. Okay, let's take a look at another example. Let's say I give you, let's see, this was a second order equation. Let's do a third order equation. Let's say y triple prime, and then let's do minus 4y double prime, and then minus 5y prime is equal to 0. So this is a third order constant coefficient linear differential equation. Yikes. But it's really not that bad to solve, right? I mean, it's the type of equation that it is just sounds ginormous, but it's pretty straightforward to solve. Okay, I go through and get the characteristic equation. What's the characteristic equation in this case? Well, again, the order of the derivative tells me the power on r, and I keep the same coefficients. That would give me r to the third minus 4r squared minus 5r is equal to 0. This would be the equation we have to solve, so let's go ahead and solve it. Let's go ahead and solve that polynomial equation. Notice that all of these have a factor of r. Factor that out. R times what's left over, r squared minus 4r minus 5 is equal to 0. And let's see, so we can, that should factor nicely. If it doesn't, let's use the quadratic formula, but it looks like it factors nicely. Product is -5, sum is -4. That would give me -5 and +1. Therefore, the solutions to this polynomial equation would be r equals 0, 5, and -1. And therefore, e to the rx, where I use each of these values of r, would be a solution to this differential equation. So let me go ahead and write what those would be. Y is equal to C1e. I'll just go in increasing order. E to the -x plus C2 e to the 0x plus C3 e to the 5x, and of course e to the 0x is 1, and that would give me y equals C1 e to the -x plus C2 plus C3 e to the 5x. So in particular, the constant function would be a solution, which makes sense because if I take y equal to 4, the derivative is 0, second derivative is 0, third derivative is 0. If I plug that function in, that is a solution to the differential equation. So this has a constant solution along with these two exponential solutions, and therefore this would be the general solution. If I go back to the previous differential equation, remember I had y double prime minus 4y equals 0. A constant solution was not a solution to this one. For example, if I say y is 4, second derivative is 0, but then if I plug in y equal to 4, this would give me -16 equals 0, which is false. Therefore, that's not a solution. Okay. So a constant is only a solution if 0 is a root of the characteristic polynomial. Okay, so as long as I can solve this characteristic equation, in other words, this polynomial equation, and I get distinct real roots, then these would be the general solution. Now, let me just kind of briefly talk about the problem if I were to have repeated real roots. Okay, so let me just kind of clean this up here. Only take me a second, so I won't pause the video. Let me just say I was to do, let's say, y double prime, let's see, plus 4y prime plus 4 is equal to 0, right? If I wanted to solve this differential equation, the characteristic equation would be r squared plus 4r plus 4 equals 0. Of course, this factors as r plus 2 squared equals 0, giving me r is equal to -2, and that is a repeated root, right? So the solutions to this would be -2, but with a multiplicity of 2. Well, if I was to just proceed as we did, say, down here, we would get, so you want to kind of leave that up there, so I'm going to kind of separate this. Okay. If I was to just proceed as follow, like we did before, we would say, well, then the general solution would be y is equal to C1 e to the -2x plus C2 e to the -2x. All right, so let's come back to that. Now look over here at this solution, which was the solution to the differential equation. This was y double prime minus 4y equals 0, right? So this was the solution to this differential equation. Notice that these two terms here are linearly independent. Therefore, they generate, the span of those two would generate the entire solution set to this differential equation. However, these two things here are linearly dependent. In fact, I could factor out e to the -2x, getting C1 plus C2 e to the negative 2x. And I could just write that as c3 e to the negative 2x. And really, I only have one solution, but I'd like to have two solutions since it's a second order, and therefore we have to figure out, well, then what do we then do? Of course, I'm not going to talk about it any further in this current video. That's going to be the content of the next video, but I at least wanted to give you an indication of, depending on, even if I have real roots, if they're repeated, we're not done. We have to add a little bit more to it, and we'll kind of see that. So go ahead and hit that subscribe button so you don't miss the next video in the series. Thank you for watching, and see you in the next one.